is going to reside into A after the subtraction process is accomplished. But when you say compare, everything is done and the flags are going to be decided and everything as if there was a subtraction process, except that the final value is not going to reside in the destination, which is the same register. So the difference now between the compare instruction and the subtract instruction is that in the subtract instruction, the value resides in the register, but in the compare instruction, the value does not reside in the register. Let's have a look at different situations here. Suppose that we're comparing A with B. If A is bigger than B, all right, what's going to happen? If effectively you're subtracting A minus B, but you're not changing the value of the accumulator. So the carry stays zero. You know, why would the carry change? If A is bigger than B, the result will be there will be no carry. If A is less than B, there is going to be a borrow at the end, at the last significant bit, or the last location, bit 7. So the carry will go high, which indicates that there is a borrow.
Is that for A greater than B or vice versa?
If A is less than B, I was talking. This is if A is less than B, the C goes to 1. The carry bit goes to 1.
Okay.
It's as if there is a subtraction process, except that the final result doesn't reside into the accumulator. Now, if A is equal to B, then what are you going to get? You're going to get a 0 as a final result for the process, but that 0 is not going to reside ultimately in the accumulator. You're
Okay.
not going to see that 0 anywhere, except that the Z flag is going to go high, indicating yes, that the outcome of comparison is as if there is two numbers are equal. That means the result of subtraction is 0. But the let's put it this way: it's an incomplete subtraction process. The comparison
Right.
process is an incomplete subtraction process. Only difference between the two is in the subtraction process, the final result resides in the accumulator.
Mm.
Let's go to the second instruction. Compare A with a value. Uh, if A is bigger than a value, yeah, I think the same thing happens here. Whether we're comparing with B or we're comparing with a value, the value could be a number in the memory, some memory location carrying some data. So everything is the same here, like the first line here. All right. Compare B with a value. Uh, yeah, same thing. Same thing. Compare D with 16 bits. Let's put it this way: they all behave the same way here, as far as these three lines are kind of similar.
Professor, what about for like so the only one that works for comparators is the C flag bits and the Z flag bits. What about
Excuse
the
me,
N flag?
could you raise your voice a little bit?
Yeah, what about for the N flag bits? Does it result in something or is it only for the C flag bits and the Z flag bits?
I couldn't understand the question. Could you repeat it?
Oh, so if let's say for example we're doing A is less than B, right? Comparing A with B,
Yes.
we get a carry is equal to 1. What about for the N flag bit? Do we get something there or no? or it doesn't matter because it's not really doing anything to the value in the register.
You're comparing A with B, and you're
Uh-huh.
worrying about the N flag.
Right.
Uh,
Do we have to worry about that or no?
okay, I think the answer is here. Let's put it this way: comparing A with B, and A is less than B, so the C goes to
Mhm.
1. It's the C that matters, not the N, because we're dealing with unsigned numbers. Remember, we're
Right.
dealing with unsigned numbers. We're not dealing with signed numbers.
Okay.
N will come into play when we deal with signed numbers,
Okay.
where the most significant bit has a meaning. But here, the numbers are unsigned, so the N doesn't come into play.
Okay.
We have a number of instructions that are relevant to that. The branch on lower and branch on higher, they are widely used in comparison of unsigned numbers. Yeah, higher and lower, it's pretty clear that we're dealing with unsigned numbers because when we say compare 7 and 5, 7 is higher than 5. As simple as that, it's we're not comparing -7 and -5, so in this case -5 would be bigger and 5 is smaller than 7, but -5 is bigger than -7. We're not getting into that issue. We're just simply comparing 7 and 5, the positive numbers. So that's where the branch on high and branch on low comes into play when you're dealing with positive numbers. Uh, so to summarize what uh, we have been talking about, and that's a very interesting summary table. You're comparing the branch on higher and branch on higher or same or branch on lower or branch on lower or the same. Branch on yeah. How is the processor gonna understand uh, your intent when you say branch if higher? How is this converted to hardware? Because the processor doesn't understand your intentions or your words or your mathematical expression. The processor responds to numbers, to flags, to signals. In case we're dealing with binary numbers here, we're talking about flags. So branch if higher. Okay, now what happens if two numbers, one of them is higher than the other? If A is higher than some value, for example, okay, what happens if A is higher than some value? The condition here, higher, is interpreted as C or Z equal to zero. Higher in our terminology is equivalent to C or Z equal to zero in the computer terminology. How is that? Because when we say higher, that means there is no carry. Carry is zero, okay? And higher means Z is zero because the answer is not zero in the accumulator. Higher means there is still some remainder in the accumulator. So both C and Z are zero. So yes, so C or Z is zero. So this logical expression is correct because when you say C or Z is zero, that means both C zero and Z zero. See? So we put them together in one equation and say, okay, C or Z is zero. As simple as that. And let's go to another one. Higher or same? Well, there is a different story here. Higher or same? It's not higher. Higher or same? Same means that there is a possibility that the result in the accumulator is going to be zero. If the two numbers are equal, there is a possibility. Yeah, there is a possibility that if the two numbers are equal, the result in the accumulator is going to be zero. So Z is going to go high. The flag is going to go high. Once the result in the accumulator is zero, Z is going to go high. So you cannot enforce this condition, C or Z equal to zero. You have to exclude Z. Z becomes a don't care condition here in the second line. So we're comparing C only because whether the numbers are, whether the accumulator is zero or whether the accumulator is positive, C is going to be zero regardless of the value of Z. Um, so that's why we excluded Z from this equation as to go from higher to higher or same. Let's do something opposite here. Branch if lower. Lower, you have to say C is equal to 1 because we need to understand what is lower opposite to. Lower is opposite to uh, higher or same, actually. Lower means the number is negative. Um, so, in other words, if A is if if you're comparing A with some value and A is smaller than that value, then the carry flag is going to go high.